So we've got our flare and blowers at one end of the system, and then we need to extend it out to the well field. So the types of piping where this is accomplished are called header, which is our kind of big highway pipe, and then lateral pipes. So lateral pipes go between the header and each well, and we might have more branching and have sublaterals and subheaders in between, but these are kind of the main groups. So header is the really big pipe, lateral is the pipe going directly to each well or trench. And commonly the header will run around the whole system in either a loop formation. So this provides some redundancy. So you can either send your gas down one side of the loop or the other if something happens to one side, or a herringbone or kind of dendritic tree formation that branches out to reach all areas of the site. And then kind of, because these systems end up being built and extended over time as the landfill cells are built and made, they end up all with really different shapes suited to the specific needs at the times when they were built. So you end up seeing really unique shapes. There's not, you don't see a lot of really uniform shapes of landfill gas collection systems. So in this figure on the side here, this is just an example of one. So there's a general loop across the site. There's a few subheaders that bridge across, which provide additional redundancy. And then we've got a few wells along a specific sublateral. We've got some branching in the middle. So all sorts of arrangements can be used, but the diameters of that piping would be designed to supply specific vacuum to handle the flow at each of these wells within the well fields. Here's an example of that header pipe. So really large diameter pipe typically, and then as it branches off, it gets smaller and smaller. And this is typically made of high density polyethylene. The header's usually in the range of 300 to 500 millimeters. So in meters, that's 0.3 to 0.5 meters. And then the laterals coming off would be more in the range of 100 millimeters. The header and lateral piping are sloped to help encourage moisture to go to places you want it to be versus places you don't want it to be. On the header, you use about a 3% slope to carry the moisture towards condensate drains, which will let the water come out of your header and not pool up and fill your pipe and cut off your vacuum. And the reason the slope is 3%, which is pretty high for construction grades, is because we're on the landfill, we know the pipe's going to move a little bit as the landfill settles. So you build a higher slope in so that even if it settles in a way that reduces the slope, you've still got a decent slope to help encourage the condensate to run down to these drains where it's going to get out of your way. Here's a schematic of one type of condensate drain. So you can see our pipe is sloping in the middle, and then it's got this drain coming down to the bottom. It's terminating in clean gravel where it would be easy to flow, and it's got this U-trap formation to prevent this end from actually sucking in landfill gas. So this whole thing's under vacuum, right? So just like on your sink, you've got this U-trap at the bottom to prevent stuff from coming back into it. So connecting on the ends of our laterals, we have our actual wells. And so we've either got vertical extraction wells or horizontal extraction trenches. Here's what the vertical wells look like. So if you've ever done anything with water wells, similar conceptual design to those. There are a few differences. So we've got this well bore going down. The annular space is filled with a filter pack material to allow the gas to flow in and not clog. We've got this well screen on our pipe that is perforated to allow our gas to come in. And then closer to the top of the well, it switches to a solid pipe, and it has a clay or a bentonite fill in the annular space to stop the gas from short circuiting between the landfill and the atmosphere. So that creates an airtight seal. At the top of the well, we have a wellhead, which has a valve that allows the flow to be adjusted. And in this photo, you can see the valve at the top of the wellhead here. And then that's connected to the lateral through a flex connection. In the picture, this is this orange hose, and that's important because the well is going to be sticking into the landfill. The waste is going to be sinking, so the ground's going to be going down around it, and then the laterals buried is going to be moving as well. So in order to stop that connection between them from breaking, use a flexible connection. And then over time, the lateral tends to fall in relation to the well, and the flex connection will get tighter and tighter and tighter. And then you'll have to come along, take off that flex connection and put a longer one on, and then just keep doing that. You even sometimes have to cut down the top of the well. So like this gray area that's sticking up, that'll poke up above the land more and more as the land settles, and eventually you'll need to cut it off and move the wellhead down just so you actually be able to reach the well. That's how much these settle over time. In the picture as well, so you can see this person on the right is holding a pump, and that could be put down the well to extract leachate, either from the very bottom or from a lens of perched leachate. And you'd use a bigger version of that kind of pump in the leachate sump to pull a continuous amount of leachate out. But you can also put them down the extraction wells if you've got too much leachate. If you have leachate kind of covering, most of your screen, then you're not going to be pulling in very much gas there. So that's where you'd want to use a pump to make sure your screen's open to be able to get as much landfill gas as you're planning to get in.